Okay, let's get started. So, 1, 2, 3, 4, 5. Okay, well, thank you for continuing to attend this course in person. One of the tricky things about videotaping all the lectures is that everybody eventually might see this lecture even if they're not in person. So, I may end up giving some of these lectures to a completely empty room, in fact. But in terms of where we are in the course, we have now completed our section that is about processing two-dimensional photographs, although we'll find that a lot of the principles we talked about in the first 3 weeks actually apply to what comes next, which is 3 weeks talking about three-dimensional surface data of the type that you would get from a radar sensor or sonar or something like that. And the 3 weeks after that will be about volumetric medical images and how to process those. So today, I'm going to talk about how we actually acquire images from 3D sensors. So I didn't actually spend much time talking about how an image is formed for photographs. Maybe I should do that. But these kinds of sensors that we're talking about are relatively more exotic. And so people tend to have less exposure to them and less knowledge about how they work. So after today, you can think, after Friday, you can think about these devices as just giving you sets of surface points or sets of 3D coordinates of objects in the real world. But today we're going to talk about how they actually get from having the sensor to getting that kind of data. So the goal of 3D sensing is to use measurements of the 3D world to recover the 3D geometry of surfaces in the world. So not just what they look like, which is what a photograph gives you, but an actual sense of their geometry. And remember, in the very beginning of the course, what I told you is one analogy is that, or one example is that if you take a photograph of my face, you get a sense of where the pixels are and where and what my face looks like. But if you get a 3D data set of my face, you actually get the shape of my nose and the contours of my lips and all that kind of stuff. So we're going to talk about that today. So your kind of punchline or your take-home message for part of this lecture is that solutions to this problem of recovering the 3D geometry of surfaces in the world fall into one of two categories, active and passive. And we all know what the terms active and passive mean in common usage. Active means that you are going out there and actually manipulating something, and passive means you're just sitting there. And the two types of sensing devices we'll talk about today fall into one of those two categories. What active means is that the sensor is actually spending energy and, in a sense, spraying energy throughout the world, sending energy outwards and waiting for the energy to come back to tell it about the structure of the real world. And a passive sensor, on the other hand, is just sitting there waiting to catch energy, and in particular catching light. So those are the two kind of principles. One is to spread energy out into the scene and wait for it to come back, and the other one is to just wait for photons, which are just kind of bouncing around and bouncing off of things all the time, waiting for some of those to fall into your sensing device. And this will give us a sense of the outer surfaces of objects, or the geometry of the boundary surfaces of objects. And again, just to remind you, in about 3 weeks we'll talk about how to actually measure the internals of an object, which is what you get from volumetric medical imaging. Any questions about where we're going? Okay. Now, most of the solutions to the 3D sensing problem are based on one of two very, very simple principles. One of them is called time of flight. And the idea here is that if I am a 3D sensing device and I emit a pulse of energy and start a stopwatch at the very same moment that I emit the pulse of energy, then I can wait for that pulse of energy to come back to me and then stop the stopwatch. And how far away the object is going to be proportional to how long it takes the energy to bounce off and come back. So you can imagine a kind of concocted example where you are in a room that is completely dark and you have a tennis ball and a flashlight. and you want to know how far away the walls are, or how far away one wall is. And you know exactly how fast you throw the ball every time. You precisely know that you can throw it at exactly 40 miles an hour. Then you can imagine that it would not be very hard for you to throw the ball and start the stopwatch at exactly the same moment. And even though it's pitch black, let's say that the ball comes right back to you. Then you can stop the stopwatch as soon as you catch the ball. And how long it took, you can back out from the math of how fast the ball was traveling, how long it took to get back to you, how far away the wall is. The other notion, the other very basic principle, we've talked about a little bit already, which is called triangulation, which is to say that if you measure the same object from two different points of view, the difference in the viewpoints can help you determine how far away the object is. And I've talked about this example when we want to model an object from video data, where we have two cameras that are some known distance apart from each other, and we're able to identify a pixel in one image that corresponds to a pixel in the other image, and we know how far apart they are from each other, so we can triangulate to say exactly how far away in the real world that object in the world is. So time of flight and triangulation are your two key, very simple principles that underlie a lot of 3D sensing. And the reason why there isn't ubiquitous 3D data acquisition in for example, in every cell phone, is that this is a simple thing in principle but difficult to implement in practice, and we'll talk about why. So, time of flight sensors. Let's see, I guess it was during World War I that the first radar detection sensors were developed. Radar is a sort of a semi-acronym of radio detection and ranging. And basically the simple idea is that there is a radar emitter that is emitting radio wave frequency energy in pulses. And usually co-located with that is a receiver. So the emitter is the thing that's throwing the energy out, and the receiver is the thing that's catching the energy. And simply put, if you had an airplane, it became widely used in World War II actually. If you were an airplane in the sky and this radio frequency energy hit your airplane, some of that energy would bounce back and go into the receiver. And so if the radar receiver detected that a certain amount of radio frequency energy was coming back to it, then it would know that it had detected an object at that particular orientation. And furthermore, it did a version of this stopwatch thing, where every time it emitted a pulse of energy, it started a stopwatch, and then stopped the stopwatch when the energy came back into the receiver. And so from that, you can tell how far away the thing is that had the energy bouncing off of it. So laser radar, or LADAR, is the same idea, but with a different frequency of emitted energy basically in the visible light region. And sonar is the same exact idea, except with sound waves traveling through water. Yeah?
Is there a difference between LADAR and LIDAR?
No. It's just who decided to use which acronym. In fact, it's laser light radar, so you can either have the lay from laser or the light from light. But I think everyone uses them exactly interchangeably. So you've probably seen, at least in a movie, submarines going through water, doing sonar, and usually the way that it's depicted in a movie is that you hear a ping, you hear an audible noise every so often. You hear bong, bong, and that's exactly what that is. It's a pulse of a sound wave that's being emitted, which corresponds to what I'm talking about here with radio frequency energy. Well, this is basically a sound wave moving through water, and really, literally what it is the emitter in that case is a speaker, as you would have on your radio system at home, and the receiver is really like a microphone. So we know how quickly sound waves propagate through a medium like water. And we do the same thing where we emit the sound, start the stopwatch, and wait. And how long it takes for sound energy, or the sound wave, to come back into the microphone tells us how far away something is. Exactly the same kind of operating principle. So there are a number of issues that make detection with radar, LiDAR, and sonar difficult in practice. So one is that I've made it sound like there's a very simple process by which a certain amount of energy is emitted, and then the same amount of energy bounces off the object and comes back. Well, that's never actually true. So because the energy that you're emitting is interacting with the molecules in the atmosphere for radar, or because the sound waves are interacting with the water molecules in sonar, the energy actually dissipates with distance. So that means that the returning energy that has bounced off of objects that are farther away is going to be less than the energy that comes from bouncing off of objects that are close to you. And in radar, one of the key concepts was the concept of signal to noise. And the idea here is that your radar receiver is going to have some low level of detection of radio frequency energy coming into it at all times. So it's just background energy that is floating around. And so the question was, what amount of radio frequency energy would we have to detect in order to assume that it's coming off of an airplane as opposed to just being part of this background? So it's this concept of signal to noise. And they developed a whole measurement methodology called receiver operating characteristics, which gives you a sense of how many airplanes you would detect if you were more or less picky with your threshold of saying, okay, I'm confident that this level of energy corresponds to an object as opposed to just the background radiation. The other problem that comes into play with these kinds of systems is scattering. So in the throwing a tennis ball against a wall example, that's a really oversimplified case because you can tell fairly easily based on the angle that the ball hits the wall how it's going to bounce off. And in fact, the tennis ball is almost certainly not going to either go through the wall or break into a million different pieces and scatter off in many different directions. But this is exactly what radio frequency energy does, or even laser light energy does, when it hits an object of interest. This is called scattering. So anytime you burst energy at an object, the actual interactions between the energy and the surface of the object are very, very complicated, and they depend on the material properties of the object and the frequency characteristics of the energy. And so only some of the energy comes straight back to the receiver, and some of it does not. And different materials have different scattering properties, as I've tried to, as I just said. So one thing that is important to at least be cognizant of when you think about 3D sensing is what's called the bidirectional reflectance distribution function, or BRDF. So the idea here is that we have emitted energy from some direction. In this case, it's light energy, but it could be from a different frequency range. And it has hit our object of interest, which is this gray thing. And then you want to know, okay, what happens to that energy? Okay, so if it's something like a mirror, then basically all of the energy that comes in is going to bounce off of it at a very well-defined angle, which you probably have learned in your physics courses, where the angle of reflectance equals the angle of incidence, right? But for any kind of realistic material that's more complicated than a very simple mirror, there's actually something that is much more complicated that goes on. Not all of the energy bounces off at that angle of incidence angle as it reflects off. some amount of it will actually go off in all of the other different directions as it interacts with the interface between the air and the object that you are bouncing the energy off of. So this is called the ambient reflection of the surface of the object. Furthermore, if you have an object like a prism, many of you are probably familiar with a prism, where what happens is that if you shine light onto a prism, only some of it reflects off, and some of it is actually transmitted through it. And that's shown here. So this is transmission, where some of the energy actually goes through the object of interest and actually hits the interface between the object and whatever's behind it. And in a simple case, let's just assume that's air. So some amount of it's going to be transmitted, and in fact, some of it's going to go all the way through the object. So, for example, the window. In fact, what you want from a window is to have as much as possible of the energy that comes in transmit right through it and go all the way through. But it's also possible for some of the energy to get through the interface between the air and the object and actually bounce off and do what's called internal reflection. That's this thing, where it gets inside the object and it gets trapped to some degree and bounces off kind of internal to the object and gets captured by it. Some of it gets absorbed, which is to say that the energy of a particular photon gets absorbed by one of the molecules inside the object, so it gets absorbed. And then, scattering and emission just basically means that instead of the energy going along a straight line as it's transmitted through the object, it actually gets scattered out. So all of these things can happen for fairly common workaday materials that you might shine a light onto or beam radio frequency energy at. And if you've ever seen a video of something like a velvet jacket, or someone walking with a velvet pair of pants, certain kinds of furs, this is one of the kind of current areas in computer graphics, actually, is coming up with compelling animations of these kinds of clothing materials. And that's because if you've ever shined a light on one of these things and tried to model how light is going to shine off of it, it's really complicated, because light can come in one point and kind of bounce around inside the thing and bounce out somewhere else. And also it has this ambient reflection thing where light that comes in one direction kind of doesn't just bounce off in the mirror type of way, but it sort of shines in all different directions. So how to model this really complicated process of energy interacting with a medium that it is beamed at is modeled by the bidirectional reflectance distribution function. And how this is modeled is that you say, well, for a particular wavelength of incoming energy, light, let's say, some amount of it reflects off in direction y. And that's what we're going to model using the bidirectional reflectance distribution function. So more mathematically, if we consider one particular location on our object of interest, and let's say that it is basically a 2D object, or you can parameterize it using two parameters, u and v. You can think of that as being the x and y coordinate of a flat thing or a position on a sphere. Then the bidirectional reflectance distribution function for a particular wavelength of the energy, lambda, is going to be some value for a particular angle of incidence, that's I, and a particular angle of output. And what this means, why there's two angles, is that if you have any direction that the light could be coming from in the 3D world, you can quantify that direction in terms of two angles, which are basically the two solid angles on the sphere. So you can think of the theta angle as being the angle where along the equator you are with respect to some zero. Let's say that this is 0, then say 90 degrees would be whoop over here, 180 degrees would be whoop over here. And then the second angle phi would be how far you go from the equator towards the North Pole. And actually, with my drawing, I think I may have that backwards. Actually, this particular figure is not very clear, I think, because there's a lot of lines going on. But just remember what I said, which is that one of the angles represents where you are along the equator, and the other one represents how far you are towards the North or South Pole. And so for every possible incoming direction of the energy, the light, let's say, and for every possible direction that light could bounce off towards, that's the output direction, there's going to be some proportion of that input energy that goes that way. And it turns out that this bidirectional reflectance distribution function depends a lot on the magnitude and the wavelength of the incoming energy and the material properties at that location UV. So a very common occurrence for someone who is just getting into 3D modeling or just getting into the video games and graphics field is for that person to propose building a 3D model of something like a coffee mug or a teapot by using this kind of 3D sensing technology. And then it doesn't work, and they can't figure out why. Well, one of the reasons why is that some types of materials have a complicated BRDF, which then makes sensing of them using 3D sensing very difficult. Any questions about this? Okay. Another problem with time-of-flight systems has to do with inner reflections. So imagine that I have a sonar device here, or it could be radar. In fact, it doesn't matter which one it is. And I have an emitter of that energy and a receiver that are co-located with each other, so they're both right here. What I told you in the tennis ball example is basically that it's pitch black and I throw a tennis ball, and I start my stopwatch when I throw it, and I stop the stopwatch when I catch the ball. But I don't really have any way of detecting the direction of travel of the tennis ball. I'm going to assume that it goes straight out of my hand and hits the wall and goes straight back towards my hand to come back. But you can imagine a more complicated case where the room is not perfectly flat and I'm not pointed straight towards the wall. And in fact, what happens is that the tennis ball bounces off of one wall, then ricochets and bounces off of another wall, and then heads back towards my receiver, or my sensor. So the problem here is that all that I've done to try to figure out how far away the walls are is started and stopped my stopwatch. And I'm going to assume that over that period of time, let's say it was a second, half of the time was spent with the tennis ball going out, and half of the time was spent with the tennis ball going back. So in fact, if this happens, and it actually takes longer for the ball to go back than I think it should, in other words, it takes longer than this back to here, then I'm going to get a false sense that the wall is actually farther away than it is, because it took the ball that much longer amount of time to go back. So this is a common pitfall in sonar especially, because what happens is that if you have a sonar detector and you take it out of water and you have it walking, you have a robot, for example, with sonar detectors on it, then a lot of times what happens is that they crash into walls in situations like this, because they have the false sense that the wall, instead of being right here, is actually further back because it took so long for this sound energy to come back to the receiver. Does that make sense? So basically what you're doing is breaking one of the fundamental assumptions of time-of-flight sensors, which is that basically that all of the energy that you emit travels out away from you in a straight line and then travels back to you along the same straight line. Okay, so another complication here is that we're greedy and we want to do 3D sensing quickly. So the simplest thing that you could possibly do if you want to, let's say that instead of just getting a sense of how far the world is away from you in this direction, you actually want to get a kind of a panoramic view of the 3D geometry of a scene. So the simplest way that you can do this is send out your burst of energy in one direction, starting your stopwatch, wait for it to come back, and then stop your stopwatch. That'll give you a sense of how far the world is away from you in this direction. Then you can rotate your sensor a little bit and do the same thing over again. Send out, wait, receive it, stop your stopwatch. So, but then, like I said, we're greedy. So we don't want to have to sit there, send out energy, and then wait at this direction for it to come back to us. We actually want to send energy, and then receive. Just basically because it's quicker. It takes too long to send and wait and send and wait and send and wait. So how can you possibly do that? Well, what you can do is identify each one of your pulses of energy so that when you catch it, you can tell what direction it was sent from. So for example, let's say that I have a way of tagging my first pulse of energy, and that's why I'm coloring it red here. So I send it out, and let's say that when it bounces off something and comes back into the sensor, I can detect that I have tagged it in that way. So in other words, this thing is tagged as being emitted from this angle. Similarly, this one, I tag it as coming from this angle, and that's why it's colored yellow. So then if I do that, and let's say that my detector can detect energy coming in at a wide range of different angles, then while I'm sending energy out over here in this part of the world, the first pulse that I emitted can come back in, and I can stop the stopwatch that I started for the red one and say, okay, it took that many seconds for the energy that I emitted at this time point to come back to the sensor from this direction. And the reason why that's faster is that instead of waiting for it to come back, I've gone on and done other stuff and waited and had it come back to me while I was doing these other things. And the way that you tag each individual pulse of energy is actually not that complicated. What you can do is very subtly change either the amplitude or the frequency characteristics of your emitted pulse of radio frequency energy to tag it in this manner. Does that make sense? Okay. So I think next I have an example. Yeah, here's an example of one such time-of-flight laser radar scanner. So it sits on a tripod. It's called the company that makes it is called QuantaPoint. It has a you can't really see it from this view. I think I have a video coming up about this, but the thing that emits the energy is an upward pointing laser that's pointed in this direction. And what it does to have it sweep across a room is that it has a mirror that's kind of pointed in this direction, so that the laser comes up like this and bounces out into the world. And then when it bounces off of something and comes back, it goes back and hits the mirror and goes into a receiver that is right next to the laser. And there's a motor that rotates this mirror and has it pitch up and down so that actually the laser can go up and down, both in the up and down direction, and it can go around like this. Oh, and in fact, there's a little diagram of it. And it can spin around very, 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 very quickly. And basically, the thing that limits how quickly it can spin around has to do with the efficiency with which you tag each one of your pulses. So you have to be able to spit out pulses that are all uniquely identifiable from each other as you are spitting them out. So let's look at one of these. Let's look at a video. So I did this in my first year of graduate school. It's basically, they call this the car barn at the university I was at. It's got a bunch of junk in it, cars and furniture and stuff. So one individual scan from this QuantaPoint scanner looks like this, where each one of those gray things is like a gives you a sense of the 3D geometry of the room. This is kind of an overhead view. And what you can do is take multiple of these scans from multiple fixed positions of the laser and align them to each other. And we'll talk about how to do that later on this week. So if you do that and you take many, many of those scans and you align them all to each other, then you can put them together into a unified 3D model of the entire room and then do something like fly through it. So this is useful for what's called as-built modeling. It should be clear that if you did this inside the Taj Mahal, then you can use the resulting 3D model for something like virtual tourism. You can also use it for games and movies. And at the time, actually, the key project that we were most interested in using this for was to do as-built modeling of the Chernobyl nuclear reactor site, the one that melted down in 1983. So, and in particular, the Ukrainian government was interested in whether the big sarcophagus that was built around the melted down reactor, whether the walls were straight up and down or whether they were starting to buckle. Well, obviously, if they're starting to buckle, that's really bad news. Any questions about this? Time of flight sensing? Okay, so one other thing to be careful about is that I've told you that, or if you kind of think about what I've told you, the only places where you get a sense of how far away objects in the real world are is by pointing one of these pulses of energy towards it. And so for something like telephone line, let's say that you're trying to fly a helicopter and do 3D sensing to avoid obstacles. Well, telephone lines are a real problem because they're almost infinitely thin from the point of view of the helicopter. And so if the helicopter is just pulsing energy and not enough of it, it's really quite likely to miss the telephone wires. And so what you have to do is basically constantly be streaming energy and spewing energy out over the scene in order to detect the telephone wires. And another thing you can do with this, having one of these sensors mounted onto a helicopter, is that you can basically classify the data as you're flying through it. So if it looks like it's very, very, like your points in the 3D world are oriented along a line, you can say, well, it looks like a linear structure such as your telephone lines would be. If it's not very linear, if the 3D points in the world are kind of all in a jumble, then you might assume that that's vegetation or something else. So one of the cautionary tales of 3D sensing is that you only find out what the structure of the 3D world is where you have decided to pulse energy out into it. This is very different than, for example, a passive sensor like a camera, where all parts of the world, from the telephone lines, from the background, from everything, send reflected light into your camera whether you like it or not. So you don't really have to worry about missing things that are very thin like telephone lines. Okay, I'm sure you all know that homework 1 is due on Friday. That's probably, well, I like to think that that's why very few people are here, actually. But, yeah.
Do you want us to print out the assignment, or do we hand that in on SmartSite?
You hand it in on SmartSite.
Okay.
And I think everyone has a Dropbox, and so you should just go to the Dropbox and then put something that's obviously named there for, to turn in your thing. And basically at the same moment that you turn in homework 1, homework 2 will appear on SmartSite for you to start working on, and it's the same program where it's due 3 weeks after it's assigned. Any questions about administrative things? Okay. Now, let's talk about triangulation sensors, which are the other approach outside of time-of-flight sensing. And for these, they're basically active and passive varieties. So active triangulation sensors are relatively exotic. Not very many people actually use them. but they tend to be quite useful in practice. So one of them, here's one possibility, and it became popular for the kind of games and movie type of audience. So in this triangulation sensor, we have a laser emitter, not a receiver, but an emitter. So all this thing does is it shoots the energy out, and it doesn't try to catch it. So that's over here, and what it's doing is it's spraying laser energy in a line through the scene, and it can rotate like this. So 1 second it can pulse the energy out in this direction, and the next it can pulse it out in this direction. So at least some of the energy, maybe not all of it, because of the complex nature of the bidirectional reflectance distribution function, but some of the energy is going to bounce off at an angle of reflection that is equal to the angle of incidence, like you're seeing here. So if we have a camera that is a fixed and known distance away from the laser emitter, then we can have that camera catch the laser energy as it's coming in, or after it's reflected off of the object of interest. So if we know where the laser energy hits the camera CCD array, and we know how far it is away from the laser, and we know what the angle of incidence is, then we can triangulate and figure out how far away this object is in the real world using simple geometry. So what this requires is that you first of all know the baseline, which is the distance between the laser and the camera. Secondly, you know to a fairly precise degree the angle that the laser emitter was at when it emitted the energy, and that you know fairly precisely where exactly on the CCD array it hit. So that will allow you to form this ray that goes from your CCD pixel out into the real world, and also to form this ray that goes from the laser emitter to the point in the real world. And you can intersect these two using simple geometry to figure out how far away the thing is. Does that make sense? Okay, here's one example. This is my former office mate using the Minolta Vivid, which is probably the most popular example of this. The laser emitter is at the top. In a second, it'll go dark, and you can see basically a line of laser. Yeah, there it is. A line of laser energy that's going brrr as the laser is scanning through the scene from top to bottom. And the Minolta are the people who made this, and they basically, at that time in the 90s, their biggest strength was that their lenses were really, really good. So they used their top-of-the-line telephoto autofocus lens, and they had it a fixed distance away from the laser emitter, and from that you're able to triangulate into the scene. So this is a 3D model of the thing that my office mate was holding at that time, and the system allowed you to take many of these 3D scans and then align them together, again using techniques that we'll talk about next week. So there are some gotchas with respect to this approach. And I remember, in fact, being in my first or second semester in grad school and trying to apply this device to a very shiny ceramic coffee pot, or a teapot. And the data looked terrible. It didn't provide the shape of the object in any kind of realistic way. And when I tried to figure out why, here was the answer. Basically, a CCD device looks like this, where you have, for each pixel, this might be 1 pixel, 2 pixel, 3 pixels, 4 pixels. And what happens is the light energy, or the provided energy, basically gets absorbed by the material that's within the CCD chip here, and it basically provides an electrical charge to it. And what happens as more and more light gets absorbed by the substrate here, or the stuff that the CCD is made out of, charge builds up, builds up, builds up, builds up, and then it acts like each pixel is like a capacitor in a way. So if enough charge builds up and builds up and builds up, then it discharges and sends a signal to the controller that says that basically how much light has been, that a certain amount of light has been detected there. And it does this very, very often, and so the more often it does it, the more bright the pixel is. But it is not always the case that each pixel has its own substrate of material that is distinct from all the other pixels. And in fact, a typical setup is like this, where there's a vertical column of pixels that are all sharing the same substrate. So imagine that you bombard one pixel here with a huge amount of electric charge, in other words, a huge amount of electric energy, or light energy. Then what's going to happen is that the charge is not going to stay in one place. It's going to diffuse. It's going to basically spread out to fill up all of this stuff. That's why it's colored pink. And you'll get the false impression that while this pixel should be perfectly bright and all the other ones should be perfectly dark, all these other ones will appear gray. And that's because you have basically overloaded the system and pumped it up full of charge before it could discharge. This shows up all the time in astronomy data, where there is one particularly bright star that should only be bright right here, but you have these streaking artifacts. It's sometimes referred to as bleeding because the charge is bleeding from one pixel to another. It's also sometimes referred to as blooming because what appears to happen is that your one point laser source, or your one point line of laser energy has kind of blossomed out into a larger thing. And that is exactly what was happening with my ceramic teapot, because I had set the energy, the emitted energy of the laser so high, and the BRDF of the ceramic teapot was such that almost all of the energy going in was reflected out like a mirror. And so it basically overloaded the CCD chip so that all pixels in the whole image appeared really overly bright because of this bleeding of electrical charge thing. By the way, for those of you who are interested in CCD chips and how they were, how they're designed and things like that, you might be interested to know that the 2009 Nobel Prize in Physics was shared by two groups of individuals. One was the fiber optics guy, the person who came up with the idea for fiber optics, and the other was the two people who came up with CCD chips in the first place. It's fascinating, actually, because the discovery of CCD technology was a complete accident. It was kind of like penicillin, where someone thought they had accidentally killed all of the microorganisms growing in their dish, when really the thing that killed it was penicillin, which was a useful thing, but it was a complete accident. In this case, what they were trying to do was build a device that removed static. They worked at Bell Labs. They were trying to build a device that removed staticky noise from a telephone conversation taking place over a landline. So they built this device that involved a set of electrical circuit elements wired up to each other. And they built it out of a particular material with this kind of a substrate. And what they found was that if they were standing a couple of feet away, their device didn't work at all. But when they leaned over it like this, it worked perfectly. And after they did that a couple of times, they figured out that the thing that was making their device work was the fact that there was no light shining on it. So then they worked out the math and they worked out the kind of engineering of it, and they determined that in fact it was the absorption of light energy that was making their circuit do a particular thing. And then that got them to thinking that that would be a useful thing. And hence CCDs kind of followed from that, the idea that just using electrical circuit elements, you can basically have a circuit that responds to the amount of light energy going in. It's a classical tale of how we stumble and trip and fall into scientific advances. But anyway, scattering is again a problem with these triangulation systems. And with lasers, for example, another thing that could have happened with my ceramic teapot example is that if I had it at the wrong angle with respect to the laser, in fact, all of the energy could have, instead of bouncing off of the object and going into my camera, it all could have bounced off in the opposite direction and I could have sensed nothing at all. So there's this kind of, you have to be in this kind of uncomfortable middle ground where you know, based on the material, that at least some of it, some of the energy going in has to emit off in the direction of the scanner. And furthermore, for something like a velvet coat that has this very complicated light scattering phenomenon, then what could eventually happen because of this scattering is that one beam of energy going in could kind of blur out into many beams of energy going out. And in fact, what that ends up meaning is that I'm not sure whether I should triangulate between this line and this one, or between this one and this one, or this one. In other words, I'm uncertain as to where exactly the position of the object is in the real world. So again, material properties can bite you. And also, if the geometry of the object is such that the energy that's emitted is not able to make its way to the camera, obviously you're going to have problems and you won't detect anything. This was actually a major problem in research that I was doing because the shape of objects tend to be complicated. And so there's always going to be a part of an object, for example, the kind of my ribs here, where if the energy is coming in like this, it's going to bounce off my arm and it's not going to make it to the scanner. Okay, so passive triangulation systems, basically the classic example of this is a multi-camera system in which you have two cameras that are a known and fixed distance apart from each other, and you are able to establish correspondences between things that appear at this pixel in this image and the same thing appearing at a pixel in this image. And by knowing the geometry or the relative geometry of the two cameras, you're able to triangulate out and detect where objects are in the real world. In terms of 3D sensing, possibly the most prominent or successful example of this is the Mars Pathfinder robots, where they actually had a stereo camera rig on each one of the rovers that was walking around on Mars, and they were able to build 3D maps of the surface of the planet and beam them back to Earth. And we've learned all kinds of different stuff about the pattern of winds and whether or not there might have been water on Mars based on the topography as was detected by this 3D sensing system. The great thing is, and the reason why they did this for the Mars robots is that energy comes at a premium. You get all of the energy you're ever going to get from your solar panels, and you have to be very stingy about how you spend it. So you have to spend your energy on moving around, sending out probes to pick up soil samples and things. So you don't want to spend all of your energy spraying laser light across the scene. So that's the big upside, is that it's passive, that you just catch photons coming in as opposed to sending energy out and waiting for it to come back. But there's real serious problems with multi-camera systems. First of all, establishing correspondences is not easy. We talked a little bit about how to do this in terms of establishing correspondences between patches in one image and patches in the other. But there's actually a textbook out there by one of the senior, very highly regarded people in this field who refers to this part of multi-camera systems as a black art. And it kind of is. That's not the most inaccurate statement. Also, cameras are complicated. So we like to have simplified models that say that light moves along a straight line from where the photon came from and goes in a straight line and hits the camera at a predictable location. But in fact, distortions in the cameras, imperfections in how the things are manufactured in the first place, and complications in the optics that try to catch light make the whole process of modeling where an object is in the real world corresponding to a particular pixel makes that very complicated. Also, there are ambiguities. So a lot of times, basically you can construct situations where if an object is moving in a particular way, it's difficult to tell without moving your head or getting a different point of view whether the thing is moving away from you or moving towards you. And then scattering, again, is another problem. So here's an example of the simplest camera model, which is actually not all that accurate in practice most of the time. It's called the pinhole camera model, where there's basically a point that we call the camera center. There's a principal point in the center of the plane, and this would be, for example, your CCD array right here. And this thing's called the optical axis, going through the camera center and the principal point. And what happens is a point out here in the real world is projected onto the camera plane somewhere such that the line of travel goes through the camera sensor. So in order to apply this simple model to your camera that you have, what you have to do is establish all of these parameters, where the optical axis is, if this is accurate and that the optical axis goes through the principal point in the camera center, and the focal length, which is to say how far the camera center is from the principal point. And if you do this wrong, your images can look like the thing on the right. And if you fail to correct for some of the inaccuracies of this model, then you end up having a poor sense of where things are in the real world. Or sorry, you get the thing on the left where that's rectangular walls, right? And they shouldn't have curves to them, but they do. I'm going to skip that. So to summarize, basically for sensing the positions of objects in the real world, you can either use active or passive approaches. And there are common problems in 3D sensing that basically have to do with complexities in how energy interacts with surfaces and sensors. And there can be ambiguities as well. Any last minute questions? Okay, thanks. See you Friday.